This is the Smart Maintenance Platform, for short SMP, provided by Atlantis Engineering. SMP acts as an assisting tool for the maintenance engineers, applying both reactive and proactive monitoring functionalities. Let's dive into the platform's component. Here, we present the data provider component, which is responsible for fetching data from the Innovas IDS connector. In the form, we provide the URL of the IDS connector, the name of the measurements for which we want to fetch data, and the periodicity of data fetching. Here is 30 seconds. The data are transformed and transferred to the data analytic tasks using a central event bus, in our case an MQTT broker, on that specific topic. Next, we move to the fault detection component, which offers reactive smart maintenance monitoring features. We have three detection options. A fault detection based on spikes, which is supported by state-of-the-art outlier detection algorithm for streaming data, called Microcluster Continuous Outlier Detection, for short MCOD. Detection based on bounds, which is a simple rule-based approach. And detection based on trends, which uses a linear regression approach to estimate the future trend of the measurements. We can deploy multiple detection tasks with different parameterizations from any of these three options running simultaneously. In the demo scenario, we report the results to a specific MQTT topic and to an influx time series database for persistence. Next, we present the failure prediction component, which offers proactive smart maintenance monitoring features. The component is based on a supervised machine learning approach, so training is needed in order to be able to predict an upcoming failure in our machinery equipment. Atlantis data scientists have already provided a set of trained models which can be used directly. The data source and the reporting sections are identical to the ones presented in the fault detection tool. The platform also allows the combination of the results of multiple detection tasks in order to construct higher-level detection strategies. For example, we might combine a detection task monitoring the first die of the press with one monitoring the second one, and only if both the tasks detect a fault on the specified range of time, only then a report is generated. This way, we can potentially reduce the false positive reports. We can manage the running tasks from the status page. Here we can see the details about each task, or we can stop one or more tasks. Since a lot of parameterization is required for all the components to work together, Atlantis data scientists developed a feature to provide all the needed parameterization using a single JSON file. Let's deploy all our tasks using this feature. All the tasks are running. The dashboard page provides multiple Grafana dashboards in order to monitor the exported results. The dashboards are useful both to the maintenance engineers and to Atlantis data scientists to assess the efficiency of the tools and, based on their results, to apply corrective actions. Let's take a look to some of the provided dashboards. In the Detection Acoustic Emission Channels Count dashboard, a plot shows the number of detected incidents per acoustic channel per detection monitoring type. The fault detection functionality is offered as an ensemble of three monitoring approaches, as no single monitoring approach is enough to accurately detect all the possible faults in the machinery. In this plot, for example, in that point, all the spikes, bounds and trend detection tasks on the RAM acoustic emission channel have reported an incident, so we are confident enough to report that something is going wrong in the machinery. We have marked the area above two incidents with red in order to clearly attract the engineer's attention. A similar dashboard with the one presented is this one, which shows the number of reported incidents per detection monitoring type for each acoustic emission channel separately. This dashboard is mostly useful for the Atlantis data scientists to assess the sensitivity of each individual monitoring type. Another dashboard with valuable information for the engineers is this one. In these plots, the actual acoustic emission value is plotted per detection monitoring type per acoustic channel, green for bounds, orange for spikes, and blue for trend. For G3 and G7, we have also plotted with purple the reported maintenance logs regarding a fault in the machinery. As we observe, the detection tool was able to detect the fault several hours before the engineer's report. For the same two cases, we showcase the ability of the Fusion tool to shrink down the report sensitivity of the detection tasks, reducing the false positive reports. Here we present the exact same scenario for the same date range. However, the monitoring types are fused by 2, producing 3 fused detection tasks: bounce fused with spikes, bounce fused with trend, and spikes fused with trend. The 2 fault incidents are still detected several hours before the actual engineer's report, and the number of reports is shrinked down from 23, which was before, to 12, and from 7 for G7 to only 1, showing that Fusion was able to shrink down the reports, still being able to detect the upcoming faults early enough. This concludes the Atlantis Smart Maintenance Platform demonstration on the Philips use case. Thank you for watching.